Oops. Hello, I'm Qifang. It's nice to be here at NCKU virtually. Okay, I hope you're all doing well. Enjoy your day. Hope you're all healthy mentally and physically. Today, I'll try to entertain you with this topic, quantum simulation via randomized product formulas. So this work was done with Xinyuan, Richard, and Joe. It's about a year ago, and this year is accepted to TQC, which is going to happen in July. And we are all at Caltech. So let's start with some very simple, or just very broad introduction. So since we're talking about quantum algorithm, presumably we're going to run it on some universal quantum computer, which is not yet, which we don't have. Okay, but anyway, if you're a programmer in the quantum computer, then you will have these gates at your disposal. Okay, so these two gates, and these are going to be universal. Universal means that you can approximate any unitary you like. It's called the Solvay-Kita theorem. You have taken a quantum computing course. But anyway, as a programmer, you actually have to build these gates and choose which one you're going to use. Okay, and you're going to benchmark your program with this various constraint that's actually very expensive. Okay, in this very expensive quantum hardware that you're going to use. So we can quantify how good our program are by the number of gates we're using and the runtime we're using, and also the number of measurements, namely how many times you're going to rerun your program. And of course, these are going to trade off with your accuracy. Okay, and on the corner is a fashionable picture of a quantum computer. And I don't know how many qubits it has, but not too many. Very expensive. Okay, so what we're talking about here is really a bit longer term research. Okay, but it's been very active. Okay, quantum algorithms. Okay, and what are we going to design these programs for? Okay, we have very powerful silicon-based computers. They can solve a hell of problems. And the new problems that quantum computer is going to solve, it starts with Shor's algorithm. Okay, so this guy is Shor. And it's going to break RSA using about 6,000 perfect qubits. Okay, this is estimate. And well, so perfect means you have appropriate error correction, which we don't really have. So we're going to use a lot more physical qubits. Okay, you have to multiply this by some overheads, which is a lot. So people think that, well, maybe this Shor's algorithm may take a while, okay, to get there. And there are simpler things we can try. I hope quantum computing can do. And maybe solve some NP problems, but maybe some of them, definitely not all of them. And some other people are looking more practically at some optimization problem. Okay. There could be some speed up, not always exponentially, but there might be some speed up. Okay, that's also possible. And today, none of these above are going to work, but people propose that we can try to solve something that at least supercomputer cannot. Okay, so this terminological quantum supremacy is just to justify quantum computers might actually do anything. Okay, this term is coined by Presco right there. And I think Google tried some 52 qubit device, but recently some other guys have claimed that their supercomputer can just do that. Okay, but of course, quantum algorithm and quantum hardwares are advancing, and it will soon that quantum supremacy will get there. Okay. But today we're not going to be talking about any of this. Okay. This is just to give you a broader sense of what other things quantum computer can do. And today we're going to talk about actually perhaps the most practical one. That's actually people do things is going to work in the near future, is to simulate quantum physics. Okay, so we're going to simulate quantum physics by quantum bits. Okay, it's called so-called qubits. So this idea actually can go back to Feynman. He's very good. He kind of have this vision about all these, and it's really coming through now. Okay, and let me just read it. It says that suppose that we try the following guess: that every finite quantum mechanical system can be described exactly, imitated exactly, by supposing that we have another system, such that at each point in space-time, the system has only two possible base states. So that's a qubit right there. Okay, and that's really the foundation of how people think about quantum computer now. So you would digitize your continuous system. So it could be some Schrödinger equation, it could be some bunch of electrons. So these are all continuous. But with appropriate digitization, you map it into a system of qubits or qubits, and then we run our program on it. Okay, so for example, one of the very strong candidates to run quantum computer on is this quantum chemistry simulation. You can ask for like energies or like thermodynamic quantities, and yeah, and so nowadays you actually have to use a lot of supercomputer to even get like somewhat realistic molecules. Okay, and of course, something that's very close to it is condensed matter systems. Okay, so for example, superconductivity, high temperature superconductivity, for example, those are very hard to simulate on supercomputer. You have to use some, I think like. I think some record is like some 30 qubits simulation. Okay, so that's very hard. Okay, it's because the space, as you know, is exponentially large. Okay, so this is what we're going to do today. We're going to simulate quantum physics. So to be more technical, here is our goal. We are given some targeted Hamiltonian. So that's H. And we want to approximate this exponential unitary evolution by some unitary we're going to assemble. And we're going to quantify our performance in terms of this error, epsilon, in this norm. So to be very precise, this is the spectral norm for matrices. So it quantifies the largest singular value. Okay, and there are also different ways to understand this metric. And you can interpret as acting on states. Okay, so you can ask what is the worst possible error you get for the worst possible state. Okay. Or operationally, you can also include effects of observables and ask for the worst states and observable. Okay. So these epsilon are actually all the same epsilon, and these notions are actually equivalent. Okay. And sometimes one of them is easier to think about than others. Okay. So sometimes people like to think about in terms of states because trace norm is pretty nice. But these are just different representations, and we're going to visit them again. Okay. And let me also mention that the ability to simulate quantum dynamics, so ability to kind of simulate this exponential IHT, is really fundamental in many of these physics application. because it can allow you, it is the building block of phase estimation. Phase estimation. So I assume you have taken some quantum computing course. Okay. Anyway, so this is pretty broad. It has a lot of application once you can simulate unitary. Cool. So how are we going to do it? How are we going to design this V? So more carefully, in our task, we're given a description of Hamiltonian to this level. So we're given that it's a sum of a few terms. And for example, it could look like h x1, x2 plus y2, y3 plus dot, dot, dot. So even these kinds, I mean, these ones that may look very simple, but it's already kind of hard to simulate on a classical device. Okay. But in a quantum computer, we're going to run it using a product of simple evolutions. Okay, what I mean simple is, so for example, these ones are going to it's going to be one of the terms. Okay. And it is your job to choose the appropriate terms to evolve for the appropriate time, okay, so that it approximates the ideal evolution. Okay, so at first glance, it's not clear how good these products are going to work. But it turns out recently that it works pretty well. So this very simple one actually works very well, and there's some kind of renaissance and kind of a booming interest to understand these product formulas. Okay. And to add a bit more details, we're going to quantify our performance in terms of the gate count. So what is gate count? Is just the number of these terms. Okay. So 1, 2, 3, da, da, da. Okay, and this is just one of the possible metric to count. There could be other different ones, but this turns out kind of capturing a lot of the things that's happened. Cool. And let me show you an example. It's a very simple one. So suppose your Hamiltonian has 3 terms, H1, H2, and H3. Okay, so for example, like X1. So this guy. Okay, so you have 3 terms. Doesn't matter what exactly they are, and the first order Suzuki formula just cycle through each term in this order. Okay, so 1, 2, 3, 1, 2, 3, and if you believe in Taylor approximation, these are going to match the first order term. It's going to match the exponential in the leading order, and up to some. Okay, so it's going to do this. So, up to some order t squared. Okay, and that t squared indeed is the actual errors. I want to do the calculation carefully. So so now you get like the gate count that's scaling about the square of time. Okay. Okay, no surprise, I guess. And let's look at these other parameters. So what's lambda? Lambda is roughly about the strength of the Hamiltonian. So it scales with t. So lambda t is dimensionless. Okay. And no surprise that the more accurate you want this to be, you need more gates. Okay, so it's inverse proportional to the error. That's fine. And what about this L? So what is L here? So L here is related to the Hamiltonian. It counts the number of terms. So here L equal to 3. Okay, so you can kind of see why there's an L here, just because you have to go through each term one by one. Okay, and in fact, this is quite a common feature of all these product formula constructions. And most of these formulas we know, even the more sophisticated one has an L there. So it has an L. It seems that these formulas just have an L. Cool. Okay, so here's just one example. Okay. And today we're going to focus on randomizing it. Okay, so the previous one is a deterministic construction. There's no coin flipping, there's no randomness. Okay. And we're going to discuss what advantage we can gain by randomizing it. Okay. And just be very careful about randomizing it because there's also quantum, so quantum also has its own randomness. And what do we mean by randomizing it? So we're going to flip some classical coins. Okay, so it's going to give you some outcomes. And these outcomes are going to be different all times. It's probabilistic. And depending on the outcome, we're going to output a random circuit. Okay, so for example, it could be like 0, 2, 1, 2. Okay, and there are many possibilities. Okay. And what we're going to ask is its performance in these different metrics we talked about. So interestingly, as it turns out, these three notions are the same in the deterministic setting, but it turns out quite different when you're randomizing it. Okay? There are some subtle issues about the orders of quantifier. It will feel very, very mysterious if you have not taken a randomized algorithm course, but we'll go through it in full details. Okay. So I just want to tell you a bit ahead that these are going to look inequivalent, okay, and they should be discussed case by case. Okay, and we're going to focus on this particular one of generating random product formulas in the simplest possible way. So here's the algorithm. You just randomly choose a term. Okay, one of the three evolves for some time and then repeat this process. Okay, so you're just going to flip a coin many times. So this one gives you 1, 1, 3, 2, 3. Okay, and you can imagine each time your coin flips is going to give you different gate sequence. And the claim is that this gives you a pretty decent product formula. It gives you pretty good performance. Okay? So it turns out it has an L advantage compared to the first order Suzuki formula. So I was telling you there's an L here, okay? But once you do randomization, you get an L improvement. And sometimes this L could be fairly large. For example, like 10,000 and just 100,000. I just quoted from Campbell's paper. Okay. So let's look more carefully what these two things are doing. So on the left, it's just 1, 2, 3, 1, 2, 3, first order formula. It goes through each term, so it has an L. On the right, what it does is a bit mysterious. So instead of doing this 1, 2, 3, you just randomly choose one of them. Okay, so there's like a 3-to-1 ratio. So it run it for a bit longer. Okay. And turns out these two have about the same accuracy. So these are up to scale. So the left one you use 6 gates, and the right one you use 2 gates. So you see that something must be coming in by taking this expectation. Okay. And you may say, well, wait a second. How come is the right thing doing any good? Because you say that, look, this one, it has sampled gate 1 and 3. But what about gate 2? So it doesn't really sample gate 2 in this case. And you can imagine in all these potential circuits, one of them is going to be missing. Okay. So how to think about this? Okay. And today we're going to look more carefully about this randomized procedure in full details. And cool. So let's get a bit more understanding of what a statement is. So I was telling you that this channel, defined by taking expectation of all possible circuits, is going to approximate your ideal unitary. But what does that actually mean? Okay, so what it means is that the measurements are close. This is an interpretation. So imagine that you're trying to do this experiment. You're trying to run QDrift. You're trying to run this randomized product formula. You input some state, okay, and you run your channel. Okay? You can randomly choose a gate sequence, and then you're going to measure some observable. And because there's statistics fluctuations, you're going to do these measurements a few times. Okay, and in the end, you kind of calculate the average. Okay. And interestingly, if you decide to open up your black box and see which gate you use, you're going to realize they're going to be different ones. Because it's generated by a random coin flip. So you might feel a bit weird that what's happening here. Sometimes these quantum mechanical averages are a bit hard to visualize, but here's really the picture. So here's your ideal evolution right here. This is ideal. And in all these QDrift, all these randomized product formula is going to spit you a random unitary evolving under state. And it could look very different states. Okay. But the point is, by taking an average, mysteriously it becomes kind of very close to your ideal evolution. Even though this guy is a mixed state. Well, these guys are pure. So by using mixed state, you get some advantage. Okay? As it seems. Okay, so here are all these heuristics. We'll present the rigorous results soon. Okay, but this is kind of the expected picture. And the main focus of this work is to understand all these typical instances. And why should we do that? And just for okay, so let's guess. Suppose they're good. If these ones are already good, so suppose they're already very close, then we don't really need to use this channel. We can just pick one of them. We can de-randomize. So de-randomize is a good thing if you can do it, okay, without sacrificing the error. And on the other hand, it is also possible that these performs poorly. Okay, so it could be kind of very far away. And that would mean that we really gain something by using a channel. Okay, so both outcomes are good, are of theoretical significance. And we're going to answer these two questions. Okay, let's move on. And here is our main results. It reads that a typical sample of product formula also works. Okay, so you just draw a sample and keep the same one. And with very high probability, you only need these gate count to ensure the unitary is very close to ideal. Okay, so a few things. So there's this extra n that's not present. So it seems that you're costing a few more gates. And second, this statement is intrinsically probabilistic. I'm not telling about some particular product formulas. I'm talking about the typical ones. Okay. And already of theoretical value, by this probabilistic argument, we found these product formulas that's independent of L. So previously, all product formula known in the deterministic sense has an L. And by randomizing it, we get rid of L and replace it with N. So what's N is the number of qubits. Okay, so L is definitely larger than number of qubits, sometimes a lot larger. And let's parse this and compare with the channel results. And okay, so there's an N and there's not an N. Okay. And the reason why we get different performances is simply because we're asking them to do different things. Okay, operationally on the left, on the statement here, this formula says is that if you sample a product formula and keep using the same one, this is the performance you get. So you're allowed to input all kinds of different states and measure all kinds of observable. And that's exactly what it means for the unitary to be close. Okay. So this explain why we will need a much longer gate sequence, because we kind of have to handle the very worst case states and observables. Cool. And in comparison, what the average channel is doing is that it's going to resample a new product formula each time you call it. Okay, so you're not talking about the performance of a particular product formulas, but the average. Okay, so each time you call it, you're going to get a different one. So for formally, this is represented as a channel. Okay, and so here's the difference. It's just whether you get to choose, whether you get fresh randomness or not. Okay. And the idea behind this is really that of a random walk on a real line. So when we're doing some coin flips, decides to go left or right. So there's going to be something called the expectation. Okay. This is some value that you can calculate. But you also realize if you flip 100 coins, it's not going to be 50-50. It's going to have some fluctuation. And the fluctuation is roughly the size square root of n. Okay. So this is also known as the central limit theorem. Okay. And this shape is exactly Gaussian. Okay. And you know that in the worst case, the coin flip can be n, but mostly it's going to only to be square root of n. And you just take this analogy and think about what we're doing when we're randomly choosing a gate. Okay, so in our setting, we're randomly choosing one among the three. It's going to have some expectation. It's going to have some drift. Okay, and also some fluctuation around the expectation. Okay, so anyway, we do this analysis and formally use some fancy tools called matrix martingales. So just because it's on a very big space, it's actually a very technical thing. And our bounds is actually also somewhat new in the mathematical world. But anyway, if you're interested, you can look at our paper. So here's a picture that has all the parameters there. So we're interested in the ideal unitary. And here is where the average channel lies in. So its error is about this. And in comparison, a typical sample has a slightly bigger deviation. It has roughly about this extra square root of n blow up. That's just about this, just coming from statistics. Okay. But interestingly, this n, what's n? N is the number of qubits so in fact is actually logarithm of the dimension of the Hilbert space. So this has something deep coming from high dimensional probability. This is actually a common feature. And the reason why these numbers comes in is because we're controlling fluctuation of a very big matrix that's of dimension 2 to the n. And we only need to pay the logarithm of that. So cool. So we kind of see some high dimensional effects coming in, but otherwise it's like a random walk. Okay. Cool. And we actually answer our questions. So how good are these guys? Well, they're good in the sense that if you make n large enough, then it does get very close to the ideal illusion. So you can in principle use this, okay? But it's also not good enough that it's not as good as the average. The average is just going to be better. Okay. But we kind of now know what's happening. And this is just a good thing to know. Okay. So you can't really de-randomize it. Okay. There's something you gain from using unitary, from using channel average. Okay, let's move on. Here comes our second main result. So remember, I was telling you there's all three different settings that was the same in a deterministic case, but become different in the randomized case. And we're going to talk about that. So on the left is the case for unitary. So in order to control the error as unitary, we have to pay this n, this price of n here. Okay. And what it amounts to is because we want it to work for all input states and all possible observables using the same sample of circuit. And interestingly, in many practical situations, you might only be interested in a state. Okay, so it might be some physical ground state they can prepare. Okay, and you can just stuck it into the same randomized procedure. And miraculously, the n disappear. So to reach the same accuracy, you don't need this n. So the depth actually decreases by a factor of 1 over n. And the only requirement for this is your state being non-random. So what does non-random mean? It means that you pick it and then you run your algorithm. So in comparison on the left, you're allowed to pick pick the worst possible state after you see this gate sequence. So there's really an order of quantifier here, and that does make a difference. So this is actually a very common thing in this probabilistic analysis, and now we're just seeing it manifesting itself in this context. Okay. And further, if you say, well, if I only care about the measurements, then you get even better performance. Okay. So if you fix some non-random state and some non-random observable, and then you run this procedure, then you only need an even shorter gate count. Okay. And this, in fact, is equivalent to channels. Okay. So that's kind of why people use channel all the time. But it's just essentially what we're saying here is to give another interpretation of what this channel bound actually means and how it compares to the different ways you're using this algorithm. Okay. So this still feels a bit very kind of, if you haven't seen these kind of arguments, it feels very weird. Okay. But let me try to explain it in the picture. So in your randomized procedure, you're just producing product formulas at random. Okay. It doesn't know about which scheme you're choosing. Okay. So each time you're just going to pick one product formula at random. And there are going to be some set of product formula that's working for some particular row and O. Okay, so it's going to have some area, and then you have some success probability. And you can choose other sets, of course, for other rows and O's. Okay, and you can do this for any other sets, and there are a lot of them. Okay, because you can choose all kinds of rows and all kinds of O's. And the point is that if you want a general purposed product formula that works for many rows and O's, then you're taking an intersection, right? And once you take the intersection, this area shrinks. Once it shrinks, you have to run more gate to make it bigger. Okay? And if you have took a probability course, this is really just the union bound. So anyway, if it doesn't make sense, that's fine. Let's move on. So what I've told you is all these different bounds, and it is another thing whether they're tight. So we also show a saturating lower bound, okay, by analytically computing this commuting Hamiltonian. Okay, so interestingly, it is commuting Hamiltonian that saturates all these behaviors, and anti-commuting ones. Okay, so not anti-commuting, non-commuting one actually helps the performance. Okay. Okay, so we also have this example in our paper. Anyway, so it's saturating them, so our bounds are really capturing what's happening. And we also try some actual examples. I think this is some very common spin chain. It has some non-commuting term. And we do see all these behavior. So there's this n behavior if you care about all the states, and the n disappear if you have a fixed input state. And then it further becomes better if you fix input state observable. So the phenomena we're bounding is, and these bounds are pretty tight, okay? Constants. Okay. So cool. We're near the conclusion now. So today I'm talking about randomizing quantum simulation. So previously there was this deterministic way of doing it, and we tried to introduce some randomness and see what happened. And it turns out you have to ask the question quite carefully. It depends on what you want these random unitary to do. And we found a very comprehensive category of these different settings that you might care about, and they have different increasing performances. And let's start reading from the left. We have this deterministic product formula that has an L, and if you just draw one random one and fix the same one to use it for many states and many observables, you get a somewhat different gate complexity that reduced in L. Okay, so this L becomes N. Okay, but you also get an epsilon squared due to like fluctuations. But anyway, these are the first product formulas that's not dependent on L. And interestingly, it further decreases if you only care about some non-random states. It's not that you need to know your states. It's just that any state that's kind of input before you choose your gate. Okay, and further, if you just pick some observable and some random state, and then you run your algorithm, and the gate count can be even fewer. And this is in fact another interpretation of channel. And this is why they're giving the same results. And we kind of, okay, so in this work, we just give a very comprehensive analysis of what it's doing. And yeah, I think this is where I should probably stop. And what else? Yeah, so in terms of outlook, actually, our same techniques work for many other randomized quantum simulation algorithm. It just works directly. And this understanding of these different settings with unitary states observably would allow us to design better randomized quantum simulation algorithm. And aside, the mathematics that's involved is actually quite new, and it will allow and so basically we now know how to analyze random product of unitaries, and it already have some applications, but I don't think I want to talk too much about them. But thank you and enjoy your day. And I don't know how I'm going to receive questions, but please have questions. And otherwise, we're welcome to see our paper. Okay? And thank you.